In this video, I'll be talking about a simple concept of process algebra, that is lever transition diagram, which is actually the most basic concept. Um, in this video, I'll be talking about lever transition diagram, which has states, transitions, actions, and in states we have initial and final states. Consider a lever transition diagram like this, which has initial state and some states in between. So this is the initial state, and there are some transitions like read, maybe action, which causes this transition from state S1 to state S2. After a read, we assume that there is a write action which will take us to a final state, a desirable state, final state indicated by concentric circles. So a simple lever transition diagram is here, which has states. The states, we have internal states or some internal states like this, and final state, which is indicated by concentric circles, and initial state indicated by arrow to a state, that is initial state. Now we know that we have drawn a lever transition diagram, but what is the advantage of lever transition diagram? Lever transition diagram is used to show a behavior of a system. Now let me consider a simple example of alarm clock, and let me see how can I depict the behavior of the alarm clock with using a simple lever transition diagram. Let me consider the alarm clock to have only two states, that is a state where alarm is set and a state where alarm is off, that is S1, and state where alarm is on. Sometime in the day, I set my alarm. Here set is action, and set my alarm, and the alarm starts to ring at the time which I have set. It's like ring is action here. For this action there is a transition, and after it rings I switch the alarm off. These are the actions and these are the states. Here alarm is off and here alarm is on. So a simple transition diagram which depicts the behavior of alarm clock. Now let me consider that I have two states and some actions which shows the behavior. Let me move further and draw. Let me add something to this diagram so that I can show you something with this diagram. Assume that in this diagram I set the alarm clock to alarm at some time. It will ring at that time, and I'll manually get up. I'll get up and manually switch the alarm off. But there may be something like an additional feature to the alarm clock, that it will ring for few time and it will turn it off automatically. That is, it will ring continuously and it will turn itself off. That is, sometimes you may have seen the alarms, like it will ring 1, 2, third time it will ring and it will stop. Alarm, it's enough, we will let me stop ringing again. It's like it goes to an off state. So what was the difference between the diagram which I had drawn before the this red line, red ring. The diagram before was like a deterministic labeled transition system, because you can see that from state S2 there was only one action that could lead to a transition, but through this red line I have two actions that can lead to I have a single action that can lead to two different transitions, that is ring from S2 will take me to S2, and ring I may also go to S1. So for a same action I can choose two paths. So this is non-deterministic. So there are two types of state transition diagrams, that label transition systems that we can draw. One is deterministic, the second one is non-deterministic. In this diagram I can consider these two states to be final state. This both can be my final state. That doesn't matter right now. So what all behavior we can show using this label transition system? Other behavior which I am going to show using a label transition system is a deadlock. Now, how can we show deadlock using a label transition system? It's really simple. That consider this label transition system which can make three actions, like A followed by B followed by C. Now from the initial state, if there is action A, it will go to state S2, and from S2 if there is action B, it goes to state S3. From S3 it goes to, with the action C, it goes to S4. Now I say that at S4 there is a deadlock. The deadlock in label transition diagram is indicated by a state which is not a final state, and the state which has no transitions to other states. If this is the case, then there is a deadlock. So S4 here is not a final state, and S4 is not having a transition to other state. So a deadlock can be represented using the simple label transition diagram. So with label transition diagram we can show behavior of a system. In the next video I will be talking about how we can compare the behavior of two given systems, that is how can we compare behavior of one system with the other.